So to start with in Lab 4, you're going to look at 4 simulations. So as usual, you go to the 1100 folder, and you look for the folder that says Lab 4, open that up, and you'll find 4 simulations in there. So I'll open up the first one. So what'll happen here is I'll click Run, and it's going to show me a little movie of a ball on a string moving in a circle. So I'll run that. And the program keeps track of what's happening with the x and y components of the velocity and also the magnitude of the velocity. So you can see how those change or don't change in time. And they ask you a few questions about this. So they say what's happening to the velocity components and what's happening to the magnitude of the velocity, the speed. Also, what's happening to the velocity vector, so that arrow that is attached to the speed. And then finally, the last question is probably the most important. Why is it that we say that this object is accelerating? Because I can stop the motion at any point, and you can see that the speed is 2 meters per second. So I can run it and stop it absolutely anywhere, and the speed is always 2 meters per second. So given that this object has a constant speed, why do we say that it's accelerating? Hint, hint, I said speed, not velocity. Think about that. So once you've answered the questions, you can go on to the next simulation. This one is going to be, again, a ball moving in a circle. The program fills in the velocity vector. As soon as I click Run, it's also going to fill in the acceleration vector. So I'll show you that. So in this case, you're looking at those 2 arrows and watching how they change over time. And there's questions on this as well. The question they ask you in question 2 is, in what direction is the velocity vector pointing, and in what direction is the acceleration vector pointing? So they mean relative to the circle, because obviously they're changing the direction over time. And in your manual, there's a sketch there. That's basically a snapshot in time of this motion, and they want you to draw in what direction the velocity and the acceleration vectors are pointed at that moment. They also want you to describe what direction they're pointed relative to the circle. So it might be useful to use phrases like tangent to the circle or towards the center. So you fill those in. And then question 3 is not actually a simulation at all. So I'm going to show you a bit of different video to explain how to do question 3, and then I'll come back and show you how to do the next 2 simulations. So question 3 is asking you to do a vector subtraction, but it specifically wants you to do a graphical vector subtraction. Not everybody's instructor actually shows them how to do this in class, so I'm just going to show you here so that you can do question 3. So this is the diagram that you've got in your book, and it's basically showing an object at 2 different times and the velocity vector at those 2 different times. So when the object was here, the velocity vector pointed like so. When the object was over here, the velocity vector pointed like so. So it changed its direction over time. So to do a graphical subtraction, what you'd need to do is, you'll have to do this by hand with a ruler and maybe a protractor if you've got one, is you take this first vector and draw it over here so that it's touching tip to tip with this other one. So I can do that very easily with the computer. I just take a clone and move it over here so it's tip to tip. Now, because this is actually supposed to be a vector subtraction, if you were doing this correctly, you would swap the direction of the arrow. So this second one would actually point back this way. But in general, what you're doing is you're going to take this first arrow and with your ruler very carefully draw it over here, same angle, same length, but touching tip to tip with this other vector. And once you've got that, then the subtraction, one minus the other of those vectors, would be the vector that connects the 2. So this red one here. And if you do it carefully, it should point towards the center, which is what we expect in uniform circular acceleration. So now you're ready to look at simulation 3 and 4, and we'll open that up. And what this is going to be is, again, balls traveling in a circle, but there's 2 of them. And you'll notice that the radius of rotation is exactly the same for these 2, but the speed is different by a factor of 2. So this will have a speed of 2 meters per second, and this will have a speed of 4 meters per second. Now, like before, when I click Run, it's going to immediately draw in the acceleration vector. And that's what we want to look at for this question, because you're going to be looking at the magnitude of the acceleration vectors and seeing how it affects things when you double the speed. So I'll click Run, and it immediately draws in the arrows, and you can see this one is quite a short arrow, this is quite a large arrow. look at the numbers, the actual values, and the question that it gets asked is, what happens to the magnitude of the acceleration when you double the speed but keep the radius the same? Look for obvious proportionality. So you look at those two numbers and you say to yourself, okay, is it twice as big? Is it half as big? Is it 4 times as big? Figure out what the proportionality is. So we doubled the speed. What happened to the acceleration? Next it asks, does the acceleration vary directly or inversely with speed? And I'll warn you that as worded, that's a bit of a trick question. So maybe go back and look at what the equation is supposed to be in your pre-lab and then figure out what the trick is. So is acceleration, does it vary directly or inversely with speed? And there's a bit of a subtlety there that you might miss. The last one is, based on the simulation, suggest an equation or proportionality statement that relates acceleration to speed. So what you would do is you'd write A for acceleration is proportional to, and then you write some function of speed. Once you've finished answering those questions, you can go on to the next simulation, which looks quite similar to this one. So simulation 4. In this case, again, we've got two balls that are going to go in circles. They both have the same speed, however. They're both at 2 meters per second for their speed, but the radius of rotation has been halved for this second one. So again, we're going to click run and we're going to look at the magnitude of the acceleration. We want to see if there's a rough proportionality, if something changes in an obvious way when you half the radius. So we click run and immediately you can see the two acceleration vectors. Look at those numbers, and again, you want to look for rough proportionality. So is it twice as big? Is it half as big? Is it 4 times as big? What happened here? You halved the radius. What happened to the acceleration? And again, they ask, does the acceleration vary directly or inversely with the radius? And suggest a proportionality statement that relates acceleration to radius. So again, A is proportional to some function of radius. And then question 6 says, suggest an equation relating acceleration to speed and radius. Hint, hint, that will look suspiciously like something you saw in the pre-lab or even in class. And then using algebra, you check that the units actually work out to be meters per second squared. Okay, this is the apparatus we're going to use for this experiment. We've got a platter that spins, and mounted on the top of the platter we have a sensor that is going to measure the acceleration of a little figurine that's taped to the top of the sensor. We also have a counterweight over here to make sure everything spins nice and evenly. And we're going to measure 3 things with this experiment. You've got a table in your manual and 3 things you need to measure. So one of them is going to be the mean acceleration felt by this little figurine. And we're going to measure that directly with the sensor in conjunction with the computer program. And I'll show you on screen how to do that in a moment. Then we're also going to measure 2 other things in order to calculate a theoretical value for the acceleration, which will then compare to the number we got off the screen. So the 2 other things you need to measure are the radius of rotation and the period of rotation, which is the time for one complete spin. So the radius of rotation is defined from being from the center of this post, so the center of rotation, over to the figurine, or if you don't have a figurine, over to the little dot with a Z beside it. So you would just grab a ruler and measure that as accurately as you can from the center of rotation to the center of either the figurine or the little dot that marks the sensor internally. To measure the period of rotation, we have a photo gate over here and a little timer that is going to do most of the work for us. So the photo gate's set up such that when the sensor swings by, it triggers the photo gate. And then this timer is going to take care of turning itself on and off automatically to measure the time for one complete revolution. So the timer should be set to pulse mode, and there's a little reset button here. You don't need to mess around with the start-stop button. It'll take care of starting and stopping itself. So you hit reset to 0 things. And the way things are set up is that when you hit reset, the first time the sensor goes by and triggers the photo gate, the timer will automatically turn itself on. When it goes by the second time, it automatically turns itself off, and then it stores that value. So we can just read the period directly off the screen in seconds. Now, before you start taking data, there's one thing that's very important that you do, and that is you need to level this apparatus. So you take your spirit level, you put it on the base, so not on the spinning part, but on the base, and you look straight down and make sure that the bubble is centered in the circle. If it isn't, the bottoms of the legs on the platform twist, and you can twist them up and down to change the leveling of the platform. So make sure it's nice and level. If it isn't level, then when you go to take data, the line on the screen, instead of looking straight, it will look wavy. So if you see a wavy line, that means you need to level things better. A little bit of a wiggle is not a big deal, but if it definitely looks like a wave, try and fix your leveling. So now we want to take data, and there's one subtlety here, and that is that when I'm going to spin this and press the collect button on the screen, and the data will start coming across the screen. It may be hard to see, but there's actually a slight downward slope to that data. That's due to friction. And that friction effect could mean that we would not get good agreement unless we're careful about how we take our data. So what I recommend you do is you give this thing a spin. Faster will give you a slightly more accurate value than slower. You'd press the collect button, you'd watch the data coming across the screen, and when it hits a vertical line where you're going to remember, hit the reset button. And the reason why is we're going to select just about 1 second's worth of data, a very small section, to calculate our acceleration value, and we want to make sure that we're using a t value that corresponds to that section of data. If you choose, for example, a t value over here and select data over here, then you might not get good agreement due to that slowdown of friction. So again, just to demonstrate, you give this guy a spin, press collect, and you watch the data. When it hits some vertical line where you'll remember, hit the reset button on your timer over here, and then you'll be able to get hopefully good correspondence between your theoretical value and your measured value. Okay, now I'm going to show you the program that you use to measure the acceleration of the figurine experimentally. So as usual, you go to the 1100 folder, and the program we're using is called Circular Acceleration. Now it's possible that this is already going to be open on your desktop because we have to get the sensor that's on the spinning platter talking to the computer. It's a wireless device. So it's possible that the technician has already set things up such that this is true. If you get this dialog box, however, that means that no, you have to tell the computer, okay, start talking to this device. So if you get this, the first thing you do is you look at your sensor, the little black box that's sitting on the spinning platform, make sure it's turned on. If it is turned on, great. Now look at the side of that black box. It's got a name written on the side of it. We have many wireless devices in the room, and if the computer finds more than one of them, you want to make sure that you tell it to talk to the one that's sitting on your desk rather than someone else's desk. So make sure you know the name of it, make sure it's turned on. If it is, then there's a button down here that says Scan for WDSS, so wireless devices basically. You click that, and it's possible that you may need to scan more than once. It's the nature of the beast. Sometimes the computer doesn't find your device right away. So if you get an error message saying it didn't find any devices, there's an option where you can rescan. So just scan again until it does find your devices. When it has found some devices, it will pop up with this dialog box, and there may be a list of devices here. Make sure that you select the one that's actually on your desk. So Franklin 27 is the one that I've got sitting in front of me. So I click OK, give it a moment to think about things, and then it should be ready to take data. Now before you take data, it's a good idea to zero things. So up here, you've got the collect button, which you'll use to take data. Right beside it is a 0. That zeroes your equipment and makes sure that the numbers you get are as accurate as possible. So with the sensor sitting still, that is with the platter not spinning, you just click this 0 button and then say OK. And again, it'll think for a second and then it's ready to take data. So you give the platter a spin at this point and you click the collect button and your data will start coming across the screen. If the data looks really wiggly, wavy, that means you didn't level your platter very accurately. I've got a little bit of a wiggle here, but that's not a big deal. In general, if you've got a faster spin, the line will be farther up the screen. A slower spin, it'll be lower down. You get more accurate values when it's high up here. It just means that you're going to get a smaller % uncertainty on your value. Now you'll remember that I said earlier that you want to watch the data coming across the screen and then hit the reset button on your timer when your data here hits some vertical line where you're going to remember where you push the reset button. The reason why is we can see a bit of a downward slope here due to friction. So to make sure our value for the acceleration isn't too affected by friction, we're only going to highlight about 1 second's worth of data. And then we're going to get our average acceleration off of that small amount of data. So to make sure that we get good agreement, that means that we want to hit the reset button on the timer pretty close to this area where we're going to highlight data. So it'd be a case of I'd give the platter a spin, press collect, and when the data hits some line that I'm going to remember, like say over here, I would press my reset button. So I'd press the reset button when it got to here, and then later, once I've got all my data, I would just highlight about 1 second's worth of data in that region where I hit the reset button. And like I said, that's just to make sure that friction doesn't cause us to not get good agreement. So once you've got this data highlighted, you then want to get the average value of this acceleration. So you can kind of come over here and get an approximate value here, but the computer will calculate an average value for this section of data for us. So you come up here to Analyze, and then Statistics, and it gives you a box that shows you what your mean acceleration value is. This is your experimental value for the acceleration on the figurine. You're also going to calculate a theoretical value using your radius of rotation and your period of rotation. And you'll compare it to this number to see whether they agree with an uncertainty.